Okay. So I'll do a little bit of summary of the Slater's rules first, and then we'll talk about the Coulomb and exchange integrals, what they mean. And then we will go from the spin orbital integrals to the spatial orbital integrals. So that is basically what I want to do today. So the summary of Slater's rules. So when you have the one electron operator, so theta 1, then when it's between the same determinants, you have a second. Then you have a sum over all the spin orbitals of the one electron part of the Hamiltonian. So for any one electron, and you sum it. Then when the two determinants differ by one spin orbital, that is m replaced by p, then the sum is gone and you only have the element between the two different orbitals. And when they differ by two or more orbitals, then you simply have 0. For the 2 electron part, you have a double sum and a half to avoid overcounting. And then you have ij. Do you remember what this notation means? It means there is ij minus. No, there's no place to write this. I will just say it. Okay. So just ij minus ji. Then when you have the determinants differing by one orbital, then one of the sums goes away and you have sum over only I, let's say, and you have the different orbital mi and pi. When they differ by two orbitals, then this sum also goes away and you are left with mn pq. And when the determinants differ by 3 or more, you have 0. So the more the two determinants are different, the simpler the value of the integral. Okay. Now from this summary, we can now directly write the energy for a single determinant. So that is basically the ultimate goal of doing all these derivations. That what is the energy of a single determinant? So the Hamiltonian now is theta 1 plus theta 2, and the energy is the expectation value between the same determinant, which is the ground state determinant. Okay. And then can someone tell me what it should be? It's pretty obvious from the Slater's rule. So which one do we need? So it's kk, this one, and this one. So it's simply sum ihi plus half sum ij. That is the energy expectation value of a single determinant.
And the minus value?
The minus value?
Means the exchange. The exchange part?
Oh, yeah, that is inside this symbol. So this is equal to, yeah?
Yes, ma'am.
Yeah. That is the notation. So I'll also write it explicitly, no problem. ij minus ji. Okay?
Yes, ma'am.
So then, yeah. So this is straightforward, the energy of the single determinant. And between these two integrals, one is called the Coulomb integral. So let's now talk about the Coulomb integral as it is called. And we will see why it is called a Coulomb integral. That is denoted by J. I'm writing AB because Zabu Osland writes AB, and that's easier for you maybe later on. So that's JAB, and then that is AB. Okay. So this first one is called the Coulomb integral, and the second one is called the exchange integral. Then why is it called the Coulomb integral? To see that, we simply have to open out the integral. So you have chi a star 1 Okay. Also, I just noticed that I am writing it in Dirac notation. I think Zabu writes it in Mulliken. So I will also write the Mulliken one over here. Okay. So it is chi A star, chi B, 1 by R12, chi A, sorry, chi A. See, this is the problem with having too many notations. No, 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 that is not right. Chi A star, chi B star, 2, chi A1, chi dx1, dx2. So this is how I would write it from the Dirac integral. And then you see that this and this together is mod chi A squared, and then you have mod chi B squared by R12 dx1 dx2. So first of all, this is always positive. And secondly, you see this is the classical integral for the Coulomb interaction between two charge clouds. So the only difference being that these are like space spin coordinates, and in a normal Coulomb charge interaction, you would have just a spatial interaction, but it's largely analogous. And also, since you can factorize out the spin part from the spin orbitals and only have the spatial part, then you are left with exactly the same thing as the classical integral for charge-charge interaction. So that is why this is called the Coulomb interaction or Coulomb integral between two charge clouds. Okay, so the Coulomb integral is pretty straightforward to understand. Now then comes the exchange integral. The exchange integral is entirely non-classical. So we do not expect that it will be easy, but we have to get some feeling. So we will try to do that. So it arises basically from the requirement of antisymmetry. So that, and it is denoted by KAB, and that is AB, BA. And in terms of Mulliken, it is also AB, BA. And this is chi A star 1, chi B star 2, 1 by R12, chi chi B1, chi A2, dx1, dx2. Okay. So here now you have electron 1 and 2 have been interchanged. So you don't have a chi A mod square or a chi B mod square. You will see there is a very innocent statement in Szabo which says that the exchange integral is also always positive. Now this is, and a lot of the conclusions afterwards relies on this, but it is not explained why it is always positive, and it is also not very easy to see why it is always positive. So the way I understand it is, if you consider this integral over all of space, so this is basically over the full charge cloud, right? So there are some contributions from all values of R12. Now the important thing to note is that the largest contributions come when R12 is small. So when R12 is small, then you have the largest contributions to the integral. Okay, and when R12 is large, you have the smaller contributions. Now, what do you mean by R1 too small? When you talk about R12 being small, it means that the R1 vector and the R2 vector are largely similar. And when they are largely similar, then why is this disappearing? Okay. And when they are largely similar, it means that chi A R1 and chi A R2 R2 are also largely similar. So then, if you look at chi A star 1 into chi A2, then this is almost the same as chi A mod square, because R1 and R2 are similar. So I am actually intentionally, I keep writing just 1 and 2 and sometimes R1 bar, R2 bar, just to enforce the fact that they are the same, okay? So they are never different. So this is basically, so is this clear to you that when R1 and R2 are similar, then chi A R1 and chi A R2 are almost the same. So chi A star 1 and chi A 2, that is almost the same as chi A mod square. So to get chi A mod square, you would have needed 1 in both places. But since R1 is similar to R2, I can write that this is similar to chi A mod square. So then we come back to sort of the expression for the Coulomb integral in a way, that is chi A. So KAB is approximately equal when R1 too small. No, I shouldn't write it like this. No, shouldn't do that. No. So the largest contributions to KAB are of the form chi A mod square, chi B mod square by R12. These are the largest contributions. Okay. And when R1 and R2 keep becoming more and more different, then of course the integral can be either positive or negative. And in that part, when it contributes to the integral, then some of it will of course cancel because of positive negative values. And even if they are, let's say, all negative, even that contribution is smaller than the large positive contribution. So overall KAB turns out to be positive. So this is not a hard and fast mathematical conclusion. This is an understanding of what the integral involves. So since the largest parts are positive and the smaller parts are either too small to destroy the sign of the overall integral, or they also cancel among themselves since they have equal probability of being positive or negative, and then the integral becomes positive. So in the Coulomb case, every element is positive in the integral. If you consider it as the integral as a sum over small elements, as you would do it numerically, for example, then every contribution is positive. But for the exchange integral, the largest contributions are positive and they overwhelm the negative contribution. Okay, that is an important difference between the two. And also, it is not a charge cloud interaction, as you can see. So it arises from the antisymmetry of the Slater determinant. If you did it with if you tried to find the energy of the Hartree product, for instance, you wouldn't get a exchange integral. Okay. Then, so do you have any questions about the physical meaning of the two, the Coulomb and the exchange integral?
Yes, ma'am. Yes.
Yes, please. Yeah, ask.
There is a condition that is R1 approximately R2. I mean that what this mean when I hear the two charge clouds are very close to each other. That's
No, there are no. This is not a. We're not. We didn't arrive at a charge cloud actually. So what it means is that when we are talking about uh, two electrons approaching each other, so when they are close to each other, uh, then the then the value of the exchange integral is positive. And the interaction is of course between two electrons is of course largest when they are close. And when they are far away, then the exchange integral can be either positive or negative.
ma'am, when if they are very far, then the Coulomb interaction always the repulsive part. So that means there is a mm,
So
uh,
the classical Coulomb interaction is always repulsive, whether they are close or whether they are far. So that is JAB.
oh,
It's always positive. It may be large, it may be small. I mean, when it's close, it's large. When it's far, it's small, but it's positive. But the
oh,
exchange integral can is positive only when they are close, and it can be anything when they are far.
okay, okay. ठीक है.
Okay. But since in an integral, the largest contribution, the sign of the largest contribution will determine the sign of the integral, then the integrated quantity is always positive. Individual contributions, so you can think of it like a series over different values of R12. Then for small R12, you have large positive values, and for small R12, you have uh, both positive and negative, but small values. So overall, the integral becomes positive. There are actually some sort of pathological cases, like you can design some
Ma'am.
wave function where the exchange integral is negative
Hello,
overall.
ma'am.
But this is not largely true for real systems. Yeah, yeah. If someone else asks the question.
Ma'am, it's me. Ma'am, when you said like for like small r, it is always positive, and for like for different r, say when r is increasing, sometimes it may be negative, sometimes it may be positive.
Hmm.
Uh, then like can we draw some like this kind of conclusion that at some large r, the electrons are attracting. I mean, it's when it is negative, exchange is negative, and at some r it is repulsing.
At some, yeah.
Since
So at some for some particular, like two particular electrons at some point of time, like one contribution, it can be negative. Yes, it can be. So they are. But this is the exchange. Remember, this is not a Coulomb interaction at all.
yeah, hypothetically, suppose like the Coulomb repulsion is like forgotten or it's removed.
Yeah, but the overall will never be
Uh-huh.
positive because you
Overall, it
have
will
the
be
J
positive.
also. The J is always positive, and the J is also larger than K.
Mhm.
So that is also there. So the net interaction, so the Hamiltonian only has this 1 by R12. Okay, so that is the physical thing. And that has contributions from both the Coulomb, the part that is going to JAB, and the part that is going to KAB. Then the net interaction between the two electrons will always be repulsive. But the exchange part can be negative as well for some gap between the two electrons. But then again, that is a momentary thing, right? If you really want to think about it classically, it is at some point of time at some two particular positions. But then again, that has no physical significance because that picture itself is what we are making up in our mind. The wave function doesn't know that, right? The wave function is not a trajectory.
Hmm.
Yeah. So that is important to understand. You will not, again, all that we do initially, it is important to understand. But when you actually get down to working things out for real problems in your research or whatever, then you have to be able to manipulate expressions basically. Okay. The physical part is only at the back of your mind. Okay, so then this is about the thing. Now we will try and go from spin orbitals to spatial orbitals. Okay. We're going to go to what happened? Spatial orbital integrals. Okay. So let us do that. So there are two types of integrals, one electron integrals and two electron integrals, where we need to go to the, oh no, here also I think Zabu writes A and B. I will also write A and B. So this is one thing. So in Dirac notation, like this, it's the same for the one electron integral. And then we will have to do the two electron. Why I keep writing ING? I think because I learned it as ING. Yes, and these two integrals we want to now write in terms of spatial orbitals. So first let us see what we call spatial orbitals. So if we have a spin orbital chi a, we can write it as in a factorized form where psi a is the spatial part. You have some spin part, let's say alpha. Okay. And there are of course hidden coordinates. So the psi a depends on r, say 1, and the alpha depends on some spin coordinate omega 1. Again, spin coordinates have no real existence, but we are just using it for convenience. And then if you have another spin orbital, okay, which I write with a bar. So the bar means that the spin part is a beta spin. So that is psi a r1 again and beta omega 2. Or beta omega 2. Okay, fine. And these two can also be written in shorthand notation as A and A bar. Lots and lots of notation. Okay. So this is the spin orbital, and we are using the bar to denote whether it is an alpha spin orbital or a beta spin orbital. And this is the spatial part, the psi, and this is the spin part, beta, if you write it explicitly. Also, here you see that for a given orbital, I have taken the spatial paths to be the same. So when the spatial paths are the same for two orbitals, for two spin orbitals, then it is called a restricted description. And if I assume that I allow my spatial paths to be different, I allow it to be different, then it is called a unrestricted description. The rest of the class we will talk about a restricted description. Okay, and afterwards, after we have done the Hartree-Fock derivation, we will come back to the unrestricted description. But now for at least the next 2 or 3 classes, we will talk about restricted description. And we will also talk about closed shell system, which means that all electrons are paired, and you have, so that again means that you have equal number of alpha and beta electrons. Fine. So now that I have written down what we want to do, we will now go into the evaluating the integral. So let's say I have A, H, A. I want to do it in Mulliken, but I keep writing it in Dirac. So if ever you see me suddenly write Dirac, just tell me that, ma'am, you have written the Dirac integral. Okay. So, okay. And then you have this. This is dx1. So now these are all the space spin coordinates. But the Hamiltonian is only spatial, but the spin orbitals are space spin. Now using the definitions for the spin orbitals, I can open them out. R1, H, R1, R1, D, R1, and then I have the integration over the spin coordinates. So since there are no bars here, they are both alpha. So alpha star omega 1, alpha omega 1, d omega 1. And the spin functions are also independently normalized. So this is 1. And I have only a spatial integral, which again has another notation, that is round brackets. And that is psi A, H psi A, okay, or A, H, A. And now these A's mean the spatial orbitals. So when there are round brackets, then if you just see a letter with no psi or chi, then they are spatial orbitals. But if you saw square brackets, or if you saw square brackets, for instance, then those are spin orbitals. And this will often be interchangeably used. People will get confused. So you have to always be careful of the context. Okay? Because when we do Hartree-Fock derivations, I think we will again write maybe the Mulliken integrals like this, but we will mean spatial orbitals. Because when you put the square round brackets, then it, especially for the 2 electron integrals, it is not clear what notation it is. Okay. Szabo claims that you use round brackets only as the analogous spatial forms of the Mulliken integrals, so the square brackets. And for the Dirac notation with the angular brackets, you don't have a separate notation for spatial integrals, so you just determine it from the context. I prefer actually using the Dirac notation myself, But for those of you who will go on to code in packages, you will see that the molecular integral is more commonly used. So I don't know, but those again from physics will be using the Dirac notation. So I am not sure which one to make you practice more. Best if you can do both without getting confused, but that is a bit difficult. Okay, anyway, so we have achieved our goal actually. So we've integrated out the spin coordinates. But why are we doing this? That is also a question. The thing is that since the spin coordinates have no actual existence, then if you want to computationally evaluate a spin integral, you cannot do it. So if you cannot ask a computer to evaluate the spin part of an integral. So you have to always remove it analytically before you code anything. So it is important to be able to write the expressions of any theory you make in spin orbitals in spatial form before you code it or use it or do whatever you want with it. Okay. So it is a very important part. Then you have, then we will do the two electron integral. That is a bit more involved now. So it's AB. And first we will separate out the. So okay, so one way of doing it is to just write all the options. So AB you evaluate, then you evaluate AB, A bar, B bar, then you evaluate AB bar, A bar, B. You can evaluate them separately. The other way is a bit smarter. This you can of course do very easily. You can just write it out and separate out the spin parts. Okay. The other way is to just take this form and see which ones will exist. So you have see, now I'm writing Mulliken and I'm writing things inside as Dirac. So that is not smart. So the Coulomb integral in Mulliken form is this. It is not AB. In Dirac form, it is AB. Okay, so there is this. So you could evaluate all four separately. Okay. And here, so do you think you can what happens if you integrate out the spin coordinates for these things? It's not actually difficult. So here you will only be left with this because all will be alpha. So you will have alpha omega 1, alpha omega 1, alpha omega 1, alpha omega 2, alpha omega 2. Okay. And then you will integrate them and you will get 1. And here you will have alpha omega 1, beta omega 1, alpha omega 2, beta omega 2. So the spin parts will integrate to 0. Okay. Here you will have all beta. So there will be, so this integral will survive. And again here you have alpha, beta, beta, alpha. So that will become again 0.
Ma'am, it will be better if you do at least one explicitly. Yes, as
Okay.
these notations are confusing.
Okay,
Not
okay.
confusing. I mean to say, I'm quite new. That's it.
Okay, okay. Thank you. I'll do it. No problem. So this is, so let's do one which is 0, because we didn't see how it turned out to be 0. All you need to do is you need to write out the full thing. So you have chi A x1 star chi A bar, which means that because of I'm putting a bar here, x1 1 by r12 chi b star x2 chi bar b x2 dx1 dx2. Okay, now if I open it out, so I get all the spatial parts. So psi a r1, psi a r1, 1 by r12. So spin, okay, I will keep writing the spin also. So from here, so this was an alpha spin, so alpha omega 1 star. Then from here you have beta omega 1 d omega 1. Then from the right hand side we have psi b star r2, psi b r2. Here you have dr1 dr2, and there is another spin integral which is alpha omega 2 star from this, and beta omega 2 from here, d omega 2. And then this is 0, this is 0. So overall the integral is 0. Okay. So in Mulliken form, basically, since this part is electron 1 and this part is electron 2, then unless they both are alpha or both are beta, you will get 0. So the other one which can be non-zero, that is A, B bar, B bar. This is non-zero. So there you would have this integral being alpha star alpha and this integral being beta star beta. So then you would have 1, 1 and you would get a non-zero integral. Okay. So this is the Coulomb integral. The various Coulomb integrals of spin orbitals in Mulliken notation. When we go over to spatial form, these are the various contributions. So now we can write the Coulomb energy term actually in terms of spatial orbitals. So let's do that. So the Coulomb part of the energy, that can be written as, let's see how to put it, let's say EJ. That was half sum AB again. I'm going over to Dirac. I will never learn. Yeah. Okay. AA BB. So in terms of spin orbitals, so maybe I'll just write it explicitly. So chi A, chi A, chi B, chi B. So this, in terms of spin orbitals, this was the Coulomb part of the energy. Now when I open it out, so every spin orbital can be barred or unbarred. This is actually not. I'm sorry, I'm trying to write it out explicitly, but there is a shortage of notation. So I'll have to skip a step and just write the full expression. I will just write it like this. Why is this not writing? Yeah, okay. So we have AABB plus A bar BB. So if I would have written all possibilities, AA bar BB bar plus AA bar B bar B plus AA bar B bar B bar. Okay. There should have been even more. Then you have the AA bar. Then the same thing with A bar A, BB plus A bar A, BB bar plus A bar A, B bar B plus A bar A, B bar B bar. So you can have many, many, many. Okay, I'm not writing all of them. But since we saw that you need to have the same spin function on the left and on the right, then we can guess which ones will survive. Okay, so this one will survive. So you have AABB. You can have A bar BB. Okay, I'll keep writing this. I'm still writing. Okay, plus AA B bar plus A bar B bar. So these are the non-zero ones. And each of them are equal to the spatial integral. Just give me 2 more minutes. It's past 10 o'clock, but I just want to finish this one line. And each of them are equal to the spatial integral. So you have 4 of them. And so you will have 2 sum over AB spatial integrals. Okay. So in terms of spatial integrals, the Coulomb contribution to the energy, so from the J part, is simply 2 times the AABB integral. Okay. So we'll do the exchange part and the total energy tomorrow then. Okay, I'll just stop here. I am not uploading this note. I will upload it together tomorrow. Okay. So someone please stop the recording.